All right, let's try it out. Inelastic collision, elastic collision. So that was pretty interesting. It seemed clear to me that we got a higher velocity for the elastic collision compared to the inelastic collision. Now let's look at applying conservation of energy for an elastic collision in more detail. So here's another take on that same question. We have toy car A and toy car B. They're going to collide in an elastic collision, but we want to know, how do we know that car A will rebound? Is there any situation in which car A will not rebound? So we set up our conservation of momentum on the left. The momentum before is only for car A. Afterward, they're both moving and we add them up. We're assuming that VA is in the positive direction. If we get a negative value for VA when we solve for it, that will prove to us that the car rebounds. Moving things around a bit, we can quickly get an expression for VB. So that is looking at conservation of momentum. Now let's look at conservation of energy. We're going to sum up the total kinetic energy before and after. And so we have 1/2 mv squared straight across. The 1/2s cancel out. And then we move things around, group-like terms, and this is what we end up with. Now, if that looks familiar on the left, a squared minus b squared is called a difference of squares, and that's equal to a minus b times a plus b. So this is what we get for our expression from conservation of energy. We now have a system of equations. We have the same variables in two equations, one from conservation of momentum, one from conservation of energy. Interestingly enough, that VB that's being squared, we have an expression for it right there. So let's put that in. And I'm just going to put that multiplied by itself and see what cancels. So we have MA is going to cancel there. This difference of terms is going to cancel there. And then one of the MBs is going to cancel there. And what we end up with is VOA plus VA is equal to MA over MB times VOA minus VA. Moving things around slightly, we get this relationship. Now let's analyze this. What does this actually tell us? Remember, we want to know, does car A always rebound? And how do we know that it rebounds mathematically? Well, if MB is bigger than MA, that implies that our numerator has to be bigger than our denominator on the other side as well. So VOA minus VA must be bigger than VOA plus VA. So we have two ratios, two fractions. We know that the mass of B is bigger than the mass of A. So if the mass of B is bigger than the mass of A, it means that our numerator on the right-hand side has to be bigger than our denominator on the right-hand side. And so you can set up an inequality and solve for VA. And what we get is VA is less than 0. In other words, VA is negative. Therefore, car A rebounds. Now note, that was for the case where mass of B was bigger than mass of A. What if it was the other way around? What if the mass of A was bigger than the mass of B? Well, if mass of A was bigger than the mass of B, then basically the inequality sign would be flipped. And what we'd end up getting would be that VA is greater than 0 or VA is positive. So in other words, if A were bigger than B, then A would keep on moving in the same forward direction. B would also move in the forward direction, but faster than A. If A is smaller than B, A rebounds. What do you think happens if they're the same mass? If you said A would stop moving and B would go off with the same velocity as A, you're totally right, and you can prove that using a similar approach with quadratic equations. Okay, so I hope that was as much fun for you as it was for me, because physics is fun. Good luck on the exams.